Why, when we have stress A and stress B at point C or point D, we get what? 0.577. Okay. Right. So I think I've bought you enough with 1 hour worth of theory. Okay. Let's apply now. Okay. Let's apply. And once we go to application, you realize that, hey, this is pretty straightforward. It's not difficult at all. Okay. So only thing that's critical is you have to know what equation to use. Okay. What equation to use. All right. Right. So now let's look at two examples first. Okay. Okay, so let's look at this example. So example number 1. By the way, you will have all this on Avenue to Learn, okay? Right. So the 1.5-inch diameter shaft is made of steel which has able to withstand 42 KSI tensile yield strength. So we are only given tensile yield strength. Using the maximum shearing stress criteria, determine the magnitude of the torque, okay, for which the torque that will occur for which P is equal to 60 kilo pound inch. Okay, but I'm not going to use maximum shear stress. In fact, I'm going to use maximum energy criteria. Okay, so we're going to look at maximum shearing stress. Maximum distortion energy, and this is going to be based on von Mises first. So we're going to do von Mises first. Then later on, we're going to do Tresca. Okay, later on, when we finish, well, then we're going to compare and see which is more conservative, or why von Mises is less conservative. Okay. So now, so what we have given, or what we are given, is the diameter is 1.5 inch. So we also know that the radius is equal to 0.75 inches, right? And the stress yield, this will be equal to 42 times 10 to the power 3 psi. And the axial load, so if I'm going to draw my axis, right, so this is my x, y, z. My load in the y direction will be equal to 60 times 10 to the power 3 pounds of force. Okay, so the first thing that we will do, we're going to base on von Mises. Right, we're going to base on von Mises criteria to find what is our T, our torque. Okay, so T over here is equal to the torque over here. Okay, so when you realize it's von Mises, you realize that, so based on von Mises, so you know that is the principal stress A squared minus by stress A stress B plus by stress B squared. Everything has to be less, right? Everything has to be less than your stress U squared. Okay, right. So now we know what is our stress U, right? Over here, we know what is our stress U. So the only thing that we don't know is what is stress A. Okay, we don't know what is our stress A. Okay, and we also don't know what is our stress B. Right. So from here, we know that we have to try to find the principal stresses at point A, or stress A and stress B. Right. So now we're going to pick an element now. Okay, so we're going to pick an element. So I'm thinking, yeah, we're going to pick an element now. Okay, so we're going to look at the stress state of an element down here. Okay, we're going to pick an element now. Okay, so from here we're going to draw our element. Right, we're going to draw an element over here. So now we sketch our element. So our element look like this now. I should have drawn more this way. I do apologize. Okay, so that's our element. So this is our stress X. So it's stress Z, stress Y, or stress Y. We know that the force is coming down. And then we have our stress Z or X. Okay, so this is our stress in our X direction. Okay, so from our structure, we know that stress X, there's no bending or whatsoever, is equal to, sorry, there's no radial forces, hook stress X is equal to 0. Stress Z is also equal to what? 0. Okay, so now we have to calculate stress Y. So stress Y is coming from the Py. So Py, sorry, I need to get out from here. Undo. Right. So stress Y is equal to minus 60 times 10 to the power 3 divided by pi r squared. All right. So stress Y in the Y direction will be 60 power 3 divided by pi divided by 175 squared. So it's equal to 33.953 times 10 to the power 3 psi. Okay. And then the next one is we have our shear, right? So the shear will be in this direction, right? So this is our shear xy. It's equal to shear yx, right? So the shear will be equal to TR over J. T is what we don't know. Okay, we want to find what is our T, right? So we don't know what is our T at all. Okay, for this case, right? So from here, we know that J, right? J is equal to I think J is pi over 2 C to the power 4, and sorry, it's TC over J, okay? And we know that C is equal to our radius, okay? But for now, we'll leave it for now, okay? We know that we need that expression over there. So from here, we can start to sketch mole circle already. Okay, we can start to sketch mole circle. This is just a sketch, okay? First, you have to come up with a sketch, and then you can see where your stress A is, stress B is, okay? So now we're going to come up with our sketch first. So we know, now we're going to do mole circle. So we know that this is our stress, normal stress. And then we have our shearing stress. I'm going to focus more on negative, is because we know that stress Y is in the negative side, okay? Right, so this is our normal stress, okay? So I'm going to label our points again. So over here, this is our point X, point Y, and this is our point Z. and we know that Z has nothing at all, so this is our point Z. Okay, and then our normal stress X will be on this line over here. Our normal stress Y, so our normal stress Y will be somewhere around here. So I'm going to do, this is our normal stress Y. Okay, so this is our stress Y, and then our shear, so our shear, okay, will be somewhere around here. Okay, so hold on. I'm going to put it over here. So this is our stress Y line. Okay, so based on the rotation of the element, right, we want to see, so we have stress X, so X, at point X, the element is going to rotate anti-clockwise. So this is our point X is, and this is our point Y is. Okay, again, I say that this is a what? This is just a sketch. Okay, so this is our mole circle. So we draw a straight line first. Okay, so we draw a straight line first. Then this is our mole circle. Okay, so this is our mole circle. So our stress average here, right? So this is our stress. So the green line is the center of circle, is a stress average. So if I'm going to complete drawing the 3D mole circle, this is how it looks like. Okay, so this is a bit here. This is one with circle. Okay, and then the other circle. This is the other circle. Okay, so this over here is for our exact plane, right? And then the other circle. No, this is not exact plane, is it? Yep, that's exact plane. So this one is our YZ plane. And the bigger circle is our XY plane. Okay, so we know now that over here, this will be our stress B point, and this is our stress A point. You need to make sure that point Z, okay, is within the circle. Okay, that will tell you that stress A and stress B, one of it is, both of them will not be equal to 0. Right? If point Z over here is outside the XY plane circle, then you can immediately assume that what, stress A is equal to what, 0, or stress B equals to 0. For this case, it will not be. Okay, that is the purpose of the sketch. Okay, so I'll write down here, sketching the mole circle. Mole circle. Okay, 3D mole circle will help. It will help to identify if any or if stress A and stress B are or is equal to 0. Stress A or stress B is equal to 0.